So those who have gone through the previous lecture, recorded lecture, okay, we have seen particular integral for the first four cases when the right hand side is of this form, or it is having this form, or it can be of this form, or maybe it will have of this form. Then we have seen that how to find the particular integral. Now today we will discuss the rest two case 5 and 6, where it can be multiplied by x to the power n and phi of x. So here was phi of x was, it was multiplied by d to the power x. Now we will have x to the power n and phi of x, or sin x in particular, sin ax and cosine of ax. And the sixth case, that will be arbitrary function of x. Okay. So these are the working formula. So we'll discuss each and every case. We have discussed the first four cases. Today we'll discuss this one. The working formula. One thing for this differential equation portion is actually here we will use too many formulas and then we will find the result. Here nothing much to explain. Just put the formula, apply it, do the calculation properly, and you will get the answer. The process may be lengthy, but it is not a difficult. You just need to follow step by step correctly. If you do that, then you will get the correct answer. So this actually you can call it a formula-based approach, formula-based topic. This particular integral. So if the function, the right-hand side is x is given as x to the power a into sin ax. In that case, we will multiply x to the power n, and we'll try to find out the particular integral for this case. And then after finding that, if we have sine function, then we'll take the imaginary part of the function. And if we have cosine, then we'll take the real part. Because we have seen that if we have 1 by f of d, x to the power n, case 2, for this case 2, we have seen if x to the power n is there, it is a function of f of d, then we will take it as upside in the numerator, and we will take the inverse, and we'll expand this as an infinite series expansion, so that it will give us one polynomial in D, and this will help us to make the derivative easier. So if you try to find out the solution for this problem, so if you note D equals to d dx and d2 equals to d2 dx2, and the given equation becomes d2y 2dy plus y equals to x into sin x. So if you take this, will give us 2d plus 1 times y equals to x sin x. Here f of d, we have d square plus 2d plus 1. Now if you take the auxiliary equation, will be m square minus 2m plus 1 equals to 0. So from here, if you solve it, what you will get? M equals to this is nothing but minus 1 whole square equals to 0. So m equals to 1 comma 1. Let us take m1. So these are repeated case. And real roots. So for this, the complementary function is given by CF is C1 plus C2 into x e to the power 1x. Okay, let us write just x. Now we know that complete solution is CF plus PI. But we have found this CF already. Now, what will be our PI? So, in order to find this PI, we need to follow the fifth procedure. So, if you remember the formula, what is that? The formula is this one. So, take this formula and apply it. So, PI is 1 by f of t x into sine x. So, here we have in place of n equals to 1, in place of a, this is also 1. Okay, if you think about, if you compare x to the power n sine ax. So if we have this case, then we will first try to find out the pi for this function. Okay. And then it will be written as follows. So this is nothing but the imaginary part of e to the power x. So directly put the formula e to the power imaginary part e to the power I ax. So here I into x, I into 1 into x, 1 by this is f of d plus I into a. A is 1 and this is nothing but x. X to the power n is here 1. Okay, so let us write it in a different way. So imaginary part of e to the power ix and f of 1 by f of d plus I. So in place of d, we will substitute d plus I because we have seen here or f of d is this one. Okay, so we will have f of d plus I is nothing but d plus I whole square minus 2 d plus I plus 1. Okay, here you put d plus I and then simplify it. You will get d square minus plus 2 di plus I square. I square will be minus 1. So let us write minus 1. And here you will write it 2d minus 2d minus 2I plus 1. So this plus 1 and this minus 1 gets cancelled. And here we have d square minus, let us take d common. Okay, so 2 is taken common, I minus 1 into d, and here remains that 2I. So for that you can substitute here now imaginary part of e to the power I x into, okay, so this is d square plus 2 I minus 1 into t minus 2y, and this is x. Okay, now what we have to do, we need to write it as a 1 plus phi of t, so that we can take inverse and we can expand it into infinite series. Okay. Then, so imaginary part of e to the power I x, from here you take 2y common, minus 2y, if you take common, then take it outside, then it becomes 1 plus I, 1 plus I, so this is becoming minus 1 plus I. No, not this. This is 1, then you get just a minute. So here you take 2y common, this 2 and this 2, just a minute. हेलो सर।
सर गुड मॉर्निंग, क्लास है क्या?
हाँ 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 सर, बोलिए सर।
क्लास में है?
हाँ हाँ ऑनलाइन ऑन क्लास। टेल मी।
क्लास only. Then I'm coming.
हाँ टेल मी सर, is it urgent?
No, no, no.
Okay, I'll call you after the class.
Okay, okay.
So this will become minus 1 plus I into t, and then 1 by 2 I into t square, and this one is already there. Sorry, this is x. Okay. Now you take it as a 1 plus or here 1 minus phi of d form. So this is a function of d, and you will take this outside on the numerator. Okay. Consider it as phi of t, because we want to make it anyone. We want to make it of this form. Our aim is to make it of this form. So that is why we will write. The next step is the pi. It is coming pi equals to imaginary part of e to the power ix 1 minus 2i. Then now we have 1 minus 1 plus I into d minus 1 by 2I into d square, and we will take it in the numerator inverse, and the quantity that is right hand side is x now. So we'll expand this into infinite series formula because only x is there. So if you put dx equals to 1, if you calculate d2x, then it becomes 0. So we need only d terms, otherwise it will be 0, because dn equals to 0 for all n. Okay, sorry, I actually muted the mic, then I forgot to. So yeah, for this case we will be getting all 0. So it is sufficient to expand this only this term. Now if you remember 1 minus x all to the power minus 1, this will go 1 plus x square plus and so on. So if you apply this formula here, then you will get imaginary part of e to the power ix 1 by minus 2I. This is there, and then we will have 1 plus 1 plus I into t, and dot dot dot. We will not write anything more, because if you write this square, then it becomes 0. Everything will become 0. So that is why you can write up to this, actually 1 plus this, because it is, we are taking it as together. So 1 by 2I d square also you can write, and plus dot dot, and the right hand side it is x multiplied. So now it becomes imaginary part of e to the power ix into 1 by 2I. Let us write it into, so x multiplied by 1, this becomes x plus, so 1 plus I into dx plus 0, all 0. So this is becoming imaginary part of e to the power ix into 1 by 2I, and this is 1 by minus 2I. This is x plus, so here it will be 1. So this is nothing but 1 plus dx is 1, so y, and everything becomes 0. Okay. So here you get, in place of e to the power ix, you can now substitute by Euler's theorem e to the power. So this is cosine of x plus I sine x. Okay. Then 1 by minus 2I into, this is x plus 1 plus I. This is x plus 1 plus I is multiplied by there. So if you again multiply by I, here also I, then it becomes minus 1, and then it becomes minus 1 and minus 1, minus 2 becomes 2. So you can write it as I by 2. Okay. So next, what we have to do is just simplify. imaginary part of, so this is I by 2 cosine x minus I into I. So minus 1. So 1 by 2 sine of x and multiplied by x plus 1 plus I. So this is just a pure simplification and you will get the answer. Imaginary part of I by 2 into x plus 1. If you multiply this, take this as together because this is a real part and this is imaginary part. So x plus 1 into cosine x, then is multiplied by this. So minus 1 by 2 cosine x. Similarly, this multiplied by this. So minus half x plus 1 into sine of x. And this multiplied by this. So this is minus I by 2 sine x. Now you just simplify it. Then it becomes, so pi equals to imaginary part of half. Take the real part and imaginary part together. Okay. So half minus half cosine of x plus, not plus, this is minus x plus 1 by 2 into sine of x. From here, this is our real part, this one and this one, real part, and these two are our imaginary part. So we'll write it as plus I times, so this is as x plus 1 by 2 into cosine of x minus I 1 by 2 sine of x. So the imaginary part of this whole term, that is this one. So pi is nothing but the imaginary part, that is this one. So x plus 1 by 2 cosine of x minus half sine of x. Hence, the complete solution Cs equals to Cf plus pi. Here you can write, that is, so now we have Cs equals complete solution. We'll write complete solution, then comma, complete solution. We indicate this y. Y as a complete solution is written as Cf plus pi. So Cf we have calculated C1 plus C2x into e to the power x plus pi is now x plus 1 by 2 cosine of x minus half sine of x. So that is our uh, final answer. Now if you remember, for the same problem, if we have where, don't forget to write C1 and C2 are arbitrary constant. Okay. Now to summarize, if we have this function, this ODE, ordinary differential equation, equals to x. Here x is x to the power n sine ax and x to the power n cosine of ax. So this part, for this we will get pi equals to, don't forget to write, imaginary part of 1 by e to the power I ax I into a into x to the power n. Similarly, for this pi will be real part. In this case, real part. So this particular problem will solve two pi's actually. Okay. So if the function is given as, in place of this x cos x was there, then also we'll apply the same formula. And then at the time of writing the final answer pi, we'll take this part, the real part. So this is our imaginary part. Okay. So real part of e to the power I ax 1 by f of d plus ia times x to the power n. Okay. So this is the fifth case. And then if you yeah, so this is your practice problem. Try to verify these four problems. Now in particular here you can see this is, it is a mixed of rule 2 and 3. If you remember this case, so here you will get, try to look at the situation here. What we are having is actually, so in this case we will have this second, this is a third case. This is 5 and this is third. Okay, here we'll have, this is 5, this is 1, and for this one you will get 4. Okay, this is a case of 5. It is a mixed type. Here is also, will apply the rule 5. Okay, so if you try to verify these results. Now the sixth problem, that is sixth formula, when the right hand side is any function of x, okay, f of t times y equals to x. So that is our given ODE, given ordinary differential equation. If the right hand side is any function of x, okay, phi of x, then we have to apply this formula. Okay, so it depends on the a. That means we need to factorize the function, so linear factors. If possible, then we will apply this formula and we will apply this method. Now as a particular example, if you see here, a is any real number. A will depend on the factor, because this f of d, okay, f of d, it is a function of like this, d power n k1 d to the power n minus 1 plus k2 to the power n minus 2 and so on, right, equals to 0. So if you factorize it, then you will get, for example, d minus a, d for d plus b. You have to factorize this function into linear factors. Also, the difficulty for this method it is if this function is not factorizable, then we cannot apply this direct formula because linear factorization. Remember, here we need linear power should be 1 and 1, d minus some c, and that should be 0. If you can make it, then we will find it. So t will be, this a value will depend on the problem. For example, for this problem, our a is 3, plus minus 3 here. Okay. Now, if you try to look at the problem, then what is happening actually? So this is our problem. It is any, although we can write it as a function of, this can be written as 1 upon cosine 3x, but this is not any of the other cases. So that is why you put it into the linear factorization. So once you have, so from the auxiliary equation you find out the values, then you make it into linear factors. So first you will try to write d square plus a. So in this way you try to write it, and then you apply the formula. So first you need to separate them by simplification. You take you do some manipulation and then simplify it. Try to make them separate. Okay. So this is d minus a, and this is d plus a type formula. And if you just apply this formula, here it is. Okay, this function. Okay. So this is the formula you have to apply depending on the value of a, and this a value will be found out by the auxiliary equation. Okay. So if you find this, apply here. So a equals to, here a equals to 3i, but for this case a equals to minus 3i. Now I apply this formula here and here also, and then simplify. So if you do this, then you will get the solution here. So try to verify this results, and then also verify these functions for arbitrary function using the rule 6. Try to verify these functions, these problems also. Now, so far we have discussed the functions that ordinary differential equations we have considered. The coefficients are actually constant type, a1, a2, all these are constant type. What will happen if we have x or x square? So that particular actually, although for higher mathematics, higher order mathematics, higher level mathematics, we have so many difficult methodologies, but here we have only simple case that is developed by Cauchy Euler homogeneous linear form. So for this type of problem, we will consider only simple ones, but the difficult ones are not part of our syllabus. So we will focus only on special type of problems, which are known as Cauchy Euler equation, homogeneous linear equations. Okay. So the expression will be looking like this. Earlier, if you go back and check, try to compare these two equations. So what we are getting here is the functions were constant. No, sorry, the coefficient here is 1. Okay, all these are actually constants. That is why there is written homogeneous linear higher order equation with constant coefficients. If the right hand side is 0, then homogeneous, and if it is non-zero, then it is non-homogeneous. Now we have to substitute, for example, x equals to e power z. Then what will be? Then logarithmic e base x is actually z. So if you differentiate it, so 1 upon x with respect to x, so dz dx. Okay. Now if you again apply the chain rule, that was dy dx is actually dy dz, and then dz dx. But for this case, we have seen this is 1 by x. 1 by x dy dz. And then you can write x into dy dx equals to, we get dy dz. Or you can write in place of, now you can write dy notation, provided d equals to d dz. Why we are doing this? Because there are functions, there are actually some differential equations which are having, yeah, here it should be 2x multiplied, it can be x square multiplied. Then the rules that we have discussed so far will not be applicable. So this particular case can be discussed with the Euler Cauchy Euler method, and they have developed this method. So if you, so we have now dy dx equals to x into dy dz. So if you differentiate again, then what will happen? d2 by dx2 d dx of x into dy dz. So this is going to be, no, sorry, this is 1 by x was there. So this is 1 by minus 1 by x square into dy dx plus, you will have 1 upon x d dx of dy dz. So for this you can write d dz into dz dx. You can write it, and then you will actually simplify it. So this is actually 1 upon x square dy dz plus, so for this one 1 upon x d2y dz 2. And if you remember, here you have 1 by x times dz dx. Okay. So for this, again you will get, if you remember, here you get digit dx, you will get 1 by x. So here you will get 1 by x multiplied. So here you get 1 upon x square dy dz plus 1 upon x square d2 by dz2. If you take it on the left side, so x square into d2 by dx2, what you will get here is actually, so here it is d2 by dz2 minus dy dz. So again you will take the d notation. If d2 equals to d2 dz2, then you get here d2y minus d into y, or you can write d minus 1 into y. Earlier we had seen this is dy. In place of x into dy, we will substitute dy, and in place of x square into d2 by dx2, we will substitute this one. Okay, so these two will need. Okay, so this one and that other one will need. So if you try to solve this problem, then what will be happening? Okay, so let e to the power z equals to x. Then you can derive all these things. Z equals to logarithmic of x, and derive all these things dz dx equals to 1 by x, and all dy dx, x into dy dx, you will get dy, where d equals to d dz, and also do all the iterations, all the calculations, then you will get x square d2y dx2, you will get d minus d into t minus 1 times y, where d2 means d dz 2, d2 dz 2. Okay, now if you substitute these values in the given equation, so this becomes, so it becomes, so this is d minus 1 into y minus 2 times x into dy dx, it becomes dy. Okay, plus, not plus, this is minus 4y was there, and in place of x to the power 4, remember, if you substitute here, because we need to do the substitution, so x to the power will be, so e power 4 z equal will be x to the power 4. So again this is e to the power 4 z. We need to do some transformation so that our well known formulas can be applied here. That's the only purpose. So if you try to write it, so the auxiliary equation, huh? So if you write it here, so this becomes d square minus d minus 2d minus 4 equals to y equals to e to the power 4z. So here you get d square minus 3d minus 4 y equals to e power 4z. Now the auxiliary equation is m square minus 3m minus 4 equals to 0. So from here you get m plus 1, then m minus 4 equals to 0. So from here you get m equals to minus 1 and 4. So distinct real roots. So the CF will be given C1 into e to the power minus 1 into, now it will be z because d we have assumed d dz. When we have assumed, it is the fact, when we have seen that the dependent variable is y and the independent variable was x, that time we had seen d dx, then CF will be CF equals to C1 e to the power x plus C1 e to the power m1 x, C2 e to the power m2 x. Now we have dz here, so this would be minus 1 into z plus C2 into e to the power 4 into z. Okay, this is our CF. So let us write C1 e to the power minus z plus C2 e to the power minus 4z. So that's what we have found. Now we want to find out the PI. So PI will be 1 upon f of t e to the power, sorry, the right hand side is e to the power 4z. Now if you write, this is coming for this formula, the first formula. Okay, now if you just try to write it, 1 upon, this is t cube, sorry, t square minus 3d minus 4 equals to into e to the power 4z. Now if you substitute a means 4, 4 square minus 3 times 4 minus 4. So this becomes 16 minus 12 minus 4. So this becomes 0. So that is why we cannot apply directly this formula. So this formula fails. So that is why we need to do, take, if this is 0, then we have to take e to the power x outside. So here we need to take z outside, and here it will be the derivative of the ft. So ft derivative. So if you differentiate this one, you will get 2d minus 3 e to the power 4z. Okay. Now you can substitute. So from here you will get z times 1 upon 2 times 4 minus 3 e to the power 4z. This is nothing but z times 1 upon 8 minus 3 e to the power 4z. So this is nothing but z into e to the power 4z by 5. Okay, right. Now complete solution, because the problem was given in terms of x, say x and y. Here the independent variable is x and the dependent variable is y. So the final answer should be in terms of x and y, not in terms of z. Z we have used to make it simplify, or we can possible the integration and other things make possible. Okay, so CF and PI. So CF we have calculated, and this is nothing but complete solution is denoted by y. So this CS comma y is equals to written as, so this is C1 e to the power minus z plus C2 e to the power 4z plus pi is z into e to the power 4z by 5. So in place of z, now we will substitute, because we have assumed, recall that we have assumed e power z equals to x. So this is going to be c1 into x to the power minus 1 plus c2 into x to the power 4 plus z. So this can be written as logarithm of x. So x to the power 4 by 5. So this is going to be final answer. Hence c1 c1 by x plus c2 into x square plus x square into logarithm of x by 5, where c1 and c2 are arbitrary constants. So this would be our final answer. So any doubt, post it. X to the power 4. Yes, yes, right, right. You are right. This is printing mistake. Okay. So that would be our final answer. And then you can solve other problems for practice problems. Verify this result. Problem 2. Another problem, you verify it. After verification, you try to solve these problems also. These are practice problems. Okay. So presently, let me just show where our actually syllabus is.